If an invisible giant were moving toward the solar system right now, when would we realize it? A black hole is not a hole in space. It is an extreme concentration of mass. Its gravity is so strong that beyond a certain boundary, not even light can escape. Most black holes form when massive stars collapse at the end of their lives, but some are far larger. At the center of our galaxy lies Sagittarius A star, a supermassive black hole with about 4 million times the mass of the Sun. Yet it is not consuming Earth because distance matters. The boundary of a black hole is called the event horizon. It is the point of no return. Once anything crosses it, no information can come back out. However, black holes do not act like cosmic vacuum cleaners. They do not automatically swallow everything nearby. If the Sun were replaced by a black hole of equal mass, Earth would continue orbiting in exactly the same way. Gravity depends on mass, not on whether that mass is a star or a black hole. Black holes are dangerous, but they are not indiscriminate destroyers. The real question is proximity. Are there wandering black holes? The center of the Milky Way galaxy is not the only place where black holes exist. Scientists estimate there could be millions of stellar mass black holes scattered throughout it. Some may have been ejected from their original systems. During a supernova explosion, asymmetric forces can launch a newly formed black hole into interstellar space. These objects emit no light, making them extremely difficult to detect. Their presence is inferred from how they gravitationally influence nearby stars. Could one of these wanderers enter the solar system? The probability is not zero, but it is extremely low. Interstellar distances are vast beyond imagination. For a random black hole to travel directly into our neighborhood would be rare, even on cosmic timescales. Still, the universe operates over billions of years. Given enough time, even unlikely events can occur. Now imagine a stellar mass black hole, roughly equal to the Sun's mass, approaching the solar system. It would contain the Sun's mass, compressed into a sphere only a few kilometers wide. It would emit no light. It would be invisible, but its gravity would be real. When would danger begin? If the black hole reached the distance of Pluto's orbit, we would first detect subtle irregularities in the motions of the outer planets. Uranus and Neptune would drift slightly from their expected paths. If it moved closer, objects in the Kuiper belt would begin to scatter. Gravitational balance would weaken. The true threat would begin once the black hole approached the interplanetary region. At that point, the Sun's gravitational dominance would no longer be secure. And when that happens, the solar system would stop being the system we know. This is only the beginning, because when a black hole arrives, the first thing it disrupts is order. The Sun contains 99.8% of the total mass of the solar system. Sun governs every planetary orbit through its gravity. Earth travels at nearly 30 kilometers per second just to avoid falling inward. Now imagine a black hole with a mass similar to the Sun entering this gravitational domain. This is not an explosion. It is not an immediate collision. It is a gravitational contest. As the black hole moves closer, its gravitational influence begins to compete with the Sun's. Planetary orbits respond instantly to changes in gravitational balance. Even small shifts in mass distribution can destabilize stable paths that have existed for billions of years. If the black hole passes near the Sun without direct collision, the solar system survives, but not unchanged. Outer planets would experience orbital distortions first. Their paths could stretch into more elliptical shapes or tilt out of alignment. Resonances between planets would be disrupted. The asteroid belt between Mars and Jupiter would likely descend into chaos. stable orbital lanes would break apart. Increased asteroid scattering would raise the probability of impacts throughout the inner solar system. Even if the black hole exits, the system would not return to its original structure. Orbital mechanics are sensitive. A single gravitational disturbance can permanently rewrite planetary paths. The solar system would remain intact, but altered. If the black hole directly captures or replaces the sun, while maintaining roughly the same mass, planetary orbits would initially remain similar. Gravity would still be present, but light would vanish instantly. Without solar radiation, Earth's surface temperature would begin dropping within days. Within a week, global averages would fall below freezing. Within a year, surface temperatures could drop to around minus 70 degrees Celsius. Photosynthesis would stop immediately. Plants would die within weeks. Food chains would collapse soon after. Oceans would begin freezing from the top down, though deep water might remain liquid for some time due to geothermal heat. The planet would not explode. It would freeze. Life on the surface would end long before orbital mechanics became the primary concern. If the black hole directly consumes the sun, the process would not be silent. As solar material spirals inward, it would form an accretion disk, a rapidly rotating structure of superheated plasma around the black hole. Friction and compression would raise temperatures to millions of degrees. This would generate intense X-ray radiation. For a brief period, the solar system could resemble a scaled-down quasar, emitting high-energy radiation far beyond normal solar output. The brightness would not come from fusion. It would come from gravitational energy conversion, one of the most efficient energy release mechanisms in the universe. Eventually, once the sun's material is consumed, the radiation would fade. What remains is a silent, invisible object with the same mass, but none of the light. At that point, the duel ends. Darkness wins. Would we truly go completely extinct, or could a few thousand people survive? If the sun's light vanishes, surface temperatures would drop below freezing within weeks. Oceans would begin freezing from the top down, forming thick ice layers. However, the deepest parts of the ocean would not freeze immediately. Geothermal heat from Earth's interior. If atmospheric escape accelerates, Earth would lose surface pressure. Even its magnetic field would not prevent long-term atmospheric loss. Under extreme gravitational stress, surface life would end within weeks or months. Total extinction is not guaranteed, but survival would not be possible on the surface. Underground cities offer a theoretical solution. Deep mines or purpose-built subterranean habitats could shield populations from radiation and extreme temperature shifts. Energy could come from nuclear reactors. Geothermal power could provide a limited but continuous source. Closed ecological systems could be constructed. Artificial lighting would enable controlled agriculture. However, maintaining such systems long-term would be technologically complex and resource-intensive. Another possibility would be pre-established space colonies. For example, if a self-sustaining settlement already existed on Mars, a fraction of humanity might survive there. However, Mars would also experience gravitational instability in this scenario. Realistically, billions could not be saved, but a few thousand, perhaps tens of thousands, might survive with advanced preparation and infrastructure. This would be a collapse of civilization, not necessarily the extinction of the species. The conclusion is direct. The surface world ends, but humanity, if prepared, might endure a little longer in the dark.